Good morning and welcome to Tech 240 for Wednesday, August 26th. The first thing I always like to do in these videos is check out the schedule, which is the first page of my binder. And it looks like today Lab 1 is due. So if you are watching this video on Wednesday, August 26th, this is a friendly reminder to submit your Lab 1. Don't forget that attachment with the picture from Tinkercad. Include that with your Lab 1. And upload that to ReggieNet by 11:55 p.m. tonight. All right, and then next time on August 31st, that's Monday, August 31st, Lab 2 is going to be due. So by 11:55 p.m. on Monday, August 31st, make sure you upload to ReggieNet your Lab 2 along with the picture of the Tinkercad circuit, the last one that you did in Lab 2. Okay? All right, so today, moving right along, we are going to continue on DC circuit analysis. And in a way, this is actually kind of the last day of what I would call DC circuit analysis, because the next time we're actually going to start talking about power and energy in electrical circuits. So, you'll get some more practice with circuit analysis in that, but power and energy, I consider that to be kind of something different, calculating power dissipation and energy consumption for electrical circuits. That's not a new tool for DC circuit analysis like what we talk about today is going to be a new tool. Okay? So today we are going to talk about a brand new tool, and I expect this is probably new for most people that take this class. I know you've seen Ohm's law before. I expect you've probably seen the power law before. So what we talk about next time might be kind of a review for lots of people. Voltage divider might have been new for a lot of people, probably, but I'm pretty sure that for most people taking this class, what we talk about today is going to be a new topic. All right, so like I mentioned in the last video, this topic tends to be a little bit more conceptually challenging than what we've done in previous classes. So what I would recommend you do, if you haven't already read the lab manual about KVL and KCL, I would really recommend you pause the video right now and go read the KVL and KCL section. It's only 3.5 pages, and then come back and watch the rest of this video. I think that seeing it written and trying to understand it that way, and then seeing it on a video will help you understand it better than just one way or the other. So that's what I'd recommend you do. But I'm going to assume at this point you have read that material, that section in the lab manual, and at least have kind of a basic grasp of what it is. And we're going to talk more about it and how to apply it in this video. All right, so let me go ahead and switch over to the document cam. Okay, let's start by talking about the way that we've done circuit analysis up to this point, and probably through Tech 111 and up through the first couple of days of Tech 240. So up to this point, we've had circuits that might look something like that, maybe as simple as that, or we can make it more complicated. We could do something like that, and we could even do more complicated than that. We could go maybe like that, and of course I'd have to tell you what the value of these resistances are, and maybe I'd also tell you what the value of this voltage is. But if I told you all of that, you could solve this. Let's say this is R1, this is R2, this is R3, this is R4, and this is R5. So what I'm going to tell you now is, if you encounter a circuit like this and you can solve it the way that we've been solving it up till now, by all means continue to do that, because that's probably the easiest way of doing it. So I'm not going to go through and solve this, but I'll tell you how I would solve it. That doesn't take very much time. What I would probably do here is reduce this down to an R total, right? I call this the method of R total, where you're going to combine all the resistances in series and parallel, and eventually you simplify it down to an R total. And once you have R total and V total, then you can find I total, and then you start working your way back out and finding everything else, right? So what you need to do here is start combining resistances wherever you can. So what I would do probably is I would say, all right, R1 and R2 are in series, and I can combine those. That might be the first thing I do. So I like to make a dashed line around here just to keep myself, clear on what I'm doing, and I would call that R equivalent 1. I'd probably then do the same thing with R3 and R4. We can combine those because they're in series. How do I know they're in series? Because whatever current passes through R3 has to also pass through R4. Same thing with R1 and R2. And I would call this one R equivalent 2. I would add those up to find R equivalent 1, add these up to find R equivalent 2, and then you could actually redraw the circuit because you've simplified it. And now what I've got is R equivalent 1, and I've got R equivalent 2, and I know what those are because I would have solved for those. And this is still R5. And now the next thing I could do, now I've just got 3 resistors in parallel. So I know the equation for that. 1 over R total equals 1 over R equivalent 1 plus 1 over R equivalent 2 plus 1 over R5. So I could solve for R total, and then I could even redraw the circuit. And now this is just R total. All right, so if I knew what V total was and I know what R total is, then I can solve for I total, and then I can start working my way back. And I can find all the individual currents and voltage drops and resistances if I don't know them already. All right, so I call that the method of R total. Basically, you are combining resistances. And you're doing that iteratively, all right? It's often going to require more than one step, just like we did here. This was step 1, this was step 2, then we got this, and then step 3 was combining all of these into an R total. So oftentimes this method is an iterative method, and it'll take you several steps to get to this, and then you have to start working your way back to find the individual current through each resistor or individual voltage drops across each resistor. And as you're doing that, you might apply Ohm's law in different cases, and you might apply voltage divider in different cases, all right, as you're kind of filling in the pieces. This whole thing kind of reminds me of Sudoku. I don't really do Sudoku. I feel like it's kind of a waste of time, but a lot of people really enjoy it. I find it kind of relaxing. My mother-in-law loves Sudoku, and when she visits our house, she always brings a whole bunch of Sudoku problems to work on. And, to each their own. That's fine. If that's how she relaxes, then that's fine. But, Sudoku is basically you fill in this kind of like mathematical puzzle, and all the pieces are related and they all fit together, right? It's almost like a mathematical crossword puzzle, right? And that's really how this kind of is. All these pieces fit together, right? As you're filling in the values for I1, I2, I3, I4, I5, V1, V2, all of them, they all interrelate. They all fit together. And so that's why it really reminds me of a Sudoku puzzle. All right, so if this works, if you are doing a problem and you get something that you see that you can combine resistances and simplify it down eventually to this, then by all means continue to do it that way, because that might be the most intuitive way. Let me give you an example. Here's lab 3. Here's a little bit of a hint on lab 3. So this is problem number 1 on lab 3. So the first question that you should ask yourself when you're doing circuit analysis problems is, can I combine all these resistances using the method of R total, method of combining resistances, and can I simplify this circuit down? And if you stare at this for a little while, think about it, then go through step by step, and probably what you'll see is that, yeah, you can actually. You can start combining these resistors. Here's a little trick. Here's a clue. Generally, the easiest way to do it is to start farthest away from the voltage source and work your way back toward the voltage source, kind of collapsing it down toward the voltage source. So the first thing I would do in this problem is I would say, all right, I'm going to combine this one and this one because they're in parallel, right? You know that because once the current gets to here, it can choose whether to go through this branch or this branch. All right, so you know these are in parallel. So I would probably combine these together and call this R equivalent 1, right? So now I've combined these into one resistor called R equivalent 1. All right, and then look at the next step. Well, what's the next thing we could do? Well, any current that goes through R4 is going to have to go through R equivalent 1, right? Because we've replaced these two with R equivalent 1, okay? So now we can say that any current that goes through R4 has to go through R equivalent 1. If it helps you, redraw this circuit, replacing these two with R equivalent 1, just like I did here. I redrew the circuit here and here. All right, so if that helps you, I would encourage you to do that. Redraw the circuit. It'll take several different steps. So the point is that any current that goes through here has to go through R equivalent 1. All right, so if that's true, then they're in series. So now I could combine all of this in series, which means I'll just take R4 plus R equivalent 1, and I will call that R equivalent 2. All right, so now you can redraw the circuit again. We've simplified it a little bit more because now what we've got is we've replaced all of these with a branch that has R equivalent 2 between here to here. All right, there's a resistance R equivalent 2. All right, so now think about how you can simplify it next. Now, what happens when the current gets to here? So it's coming from the voltage source, going through R1, it gets to here. Now the current has a choice. It can go either through R3 or it can go through R equivalent 2 and back to here, right? So if it has a choice, then what's that tell you? It's in parallel. So I can combine R3 and R equivalent 2 in parallel. So I'm going to combine these again, and I'll call that R equivalent 3. All right, so now I've replaced all of these resistances with one resistor that we call R equivalent 3. All right, and now hopefully you can see that whatever current comes through R1 has to go through R equivalent 3, and then it comes back to here and it has to go through R2. So that tells you that R1 is in series with R equivalent 3, which is in series with R2. So now you can just add them up in series. The next step would be R total. R total equals R1 plus R equivalent 3 plus R2. Now you've got R total, you've already got V total, so you can find I total. All right, that's I total. I'm going to tell you one more clue about this. I've already given you some pretty good clues about this problem, but I'm going to help you out with one more thing that sometimes students have some trouble with. So now you've got R total, you've got V total, so you can find I total, right? So you've got I total. All right, I total is known. So what is I total? I total is the current coming out of this voltage source. So I total is coming out right here. This is I total. All right. So are there any values of current, are there any component current values that you know without having to do any more calculation? There are, actually. There are. Because if you know the current coming out here through this wire, then you know the current going through here, and you know the current going through here. So as soon as you know I total, you already know I1. So there's really no calculation to be done to find I1 once you know I total, because whatever current comes out here, there's no other place for that current to go. You know, this wire is not leaking charge, and there's no charge being added to it in this wire. So whatever current is flowing here must be flowing here and must be flowing through this resistor. All right, through here. So as soon as you know I total, you know I1. They're the same, right? Okay, so you know I1. Now that doesn't necessarily help you find the current going through any of these. You know, it doesn't help you find I3 or I4 or I5 or I6, but you do know what I equivalent 3 is, right? So R equivalent 3 is not a real resistor. It's a fictional resistor that represents all of these. But that could be useful later on. Make note of that. You know what I equivalent 3 is. And what else do you know? There's one more thing that you know right off the bat, right? So whatever current comes through here, I1, some of that goes through here, some of that goes through here and here, some of it goes through here and here, but all of it has to meet back up right here, right? And then it has to come through here, and through here, and then back to the negative side of the source, right? Whatever current flow is coming out of the source is the same as what you have coming into the source. Okay, so whatever current is going through here, you don't know what's going through here or here or here or here yet, but you do know that all of that meets back up here, and so your same value of I1 has to come back through here and must come through here, which is resistor 2. So what I'm saying is that as soon as you know I total, you automatically know I1 and you know I2, just based on the way this circuit is configured. All right. Okay, so that's a pretty big help. I think that will help you quite a bit. All right, so that's a significant portion of number 1 on lab 3 that I just helped you out with. So I hope that is a help. All right, but there are going to be times when that doesn't work. For examples of that, just look at the rest of lab 3. Or here, I'll draw a circuit right now that we can take a look at. All right, so let's say that's a voltage source, and let's say I've got a resistor here and a resistor here, and then let's say I've got a resistor here. And so far so good. That's not intimidating. These are in parallel, and then I can combine those, and then this combination is in series with this, right? So no biggie so far. That's pretty easy. But what if I do this? Another voltage source, which is not as uncommon as it sounds. So now I have 2 voltage sources, and I still have these same resistances. All right, so it's still true that these are in parallel, right? Because when the current gets here, it could go through either of these branches, right? So you could combine these in parallel still. But the problem is after that, because you can no longer say that this combination is in series with this. Because let's say we combine those into one equivalent resistor, and then it gets here. We can no longer say that all the current coming through this equivalent resistor goes through here. Because it's possible, first of all, that some of the current coming from this voltage source is going to go through this resistor. So the current through here might be different than the current going through this equivalent resistor right here. It's also true that some current going through here might actually be going this way and forcing its way backwards through the voltage source. That can happen. That's how you charge a battery. If this was a battery, and we forced current backwards through it, we would be charging the battery. That's exactly how you charge a rechargeable battery. So this is a problem. We don't know how to do this yet. the method of equivalent resistances is not going to work here because we cannot combine all these resistances, because we cannot say that this combination is in series with this. So we're stuck for now. But I'm going to show you another way using another tool. So I just want to emphasize, this is just, what I'm going to show you today, this is just another circuit analysis tool, all right? It's not like some exotic magic thing. It's really, I mean, it's kind of similar to Ohm's law in the sense that it's just a tool that you can apply to circuits to solve for component currents and component voltage drops and things like that. And the tool that we're going to talk about today, two of them actually, they're related. One of them is called Kirchhoff's voltage law, and we always abbreviate that KVL because Kirchhoff's voltage law is a mouthful. And the second one is Kirchhoff's current law, which we abbreviate KCL. All right. So you can probably imagine Kirchhoff was a scientist. His name was Gustav. Gustav Kirchhoff was a German scientist who studied actually thermodynamics and also electricity in Germany in the mid-1800s. And he's given credit for developing these concepts, and so the laws are named after him. All right, so let me tell you a little bit about what they are, and then we will apply them, okay? So let me do a brief description of what they tell us, and then we'll actually apply it to a problem, okay? So first of all, we have KVL. And let me motivate this a little bit by saying, let's say that we have a circuit, and this voltage source is 12 volts. And let's say that, okay, this is a super simple circuit, all right? This is, don't overthink this, okay? What is V1? What is the voltage drop across resistor 1? All right? So I know that I have, here's my multimeter, all right? I know that if I measure the voltage gain from here to here, it's going to give me 12 volts because it's a 12 volt source. I've also told you in the past that for our purposes, we're going to basically ignore the wires because the wire has negligible resistance for our purposes. These small little circuits have negligible resistance in the wires. So if I don't have any resistance in the wires, then I have no voltage drop in the wires. So if I gain 12 volts here, what do you think my voltage drop is from here to here? It's got to be 12 volts. There's no other place to drop voltage in this circuit other than through resistor 1. So V1 has got to be 12 volts. There's no other choice, right? All right, let's do just a slightly more complicated circuit. Let's still say we've got a 12 volt source. Let's say I've got two resistors, and this is R1, this is R2. It doesn't matter what the values of the resistances are. I'm not even going to tell you them to muddy the water, but let's say I tell you that V1 equals 6 volts. All right? And the question is, what's V2? Okay, so what I'm saying is that in this circuit, when I measure the voltage gain from the negative to the positive side of the battery, I get 12 volts. So we gain 12 volts here, from here to here. And I know that we don't drop any voltage in the wire, or wires. And I know that we drop 6 volts from here to here. And now I'm asking you, what voltage do we drop from here to here across R2? Right? So I think it's fairly intuitive to say that, well, if we gain 12 here, we don't drop anything in the wires, and we drop 6 here, then whatever is left must be dropped here, from here to here. And that's exactly right. Yeah, V2 must be 6 volts. All right, now forget that. Let's say that V1, I'm telling you that V1 is equal to 3 volts. All right, so whatever the value of resistance is, I don't care right now, but I'm telling you that the drop from here to here is 3 volts. All right, we've still got 12 volts gained from here to here. Still don't drop any voltage in the wires. So once again, whatever is left over must be dropped right here. Right? So I gained 12 here to here. I dropped 3 from here to here. The only place left to drop voltage is from here to here. So it's whatever's left. 12 minus 3 equals 9. So V2 must equal 9 volts. And that's exactly right. Okay? That's basically KVL. That's Kirchhoff's voltage law. I'm gonna tell you how to write those equations. This was pretty intuitive, but there's a formalized way to write that equation so that you would get 6 volts or 9 volts. All right. So I'm gonna give you the way to write that equation. Okay. So let's go ahead and write it in words first. All right. So what KVL? I think I have room down here. What KVL says is that the sum of voltage drops around any closed loop in a circuit is 0. All right. Right now, it may not be intuitive. You're saying, I don't really get how we went from this to this. But we did because we gained 12 here, right? So we gained 12 volts. Then we dropped 3, and then we dropped 9. All right. So our voltage drops add up to our voltage gain. Okay. So the net is 0. The sum of voltage drops. We dropped 12 and we gained 12. So the sum of the voltage drops was 0. All right, so I'm going to give you a way to actually write those equations and not have to rely on intuition, because intuition will bite you. So write the equations the way I'm going to tell you in a little bit. All right, but next I'm going to do a brief motivation of KCL. All right, so to motivate KCL, let's say this might almost be too simple. The first example I give you may actually be too simple. It might be confusing because it's too simple. All right, so let's say this is R1, this is R2, and let's say I know what I1 is, and let's say it's 1 amp. And let's say I want to know what is I2. What's I2? All right, we've got a node right here. A node just means a place where 2 or more wires are coming together. And I know that 1 amp is coming through resistor 1 into the node. And there's only 1 wire coming out of the node, and it goes into R2. So we have current through R2, which is I2. So what is I2? Well, these are in series, but more importantly, to kind of motivate KCL, I've got 1 amp coming into this node, and I've only got 1 wire coming out of that node. So whatever comes in here must also come out here. There's no, like I said earlier, there's no charge being lost or leaked out anywhere, and there's no charge being added into the circuit anywhere except a voltage source. Okay, so this must also be 1 amp. I mean, it's almost too simple, right? But let's go just a tiny bit more complicated. Let's say now this is R1. This is still R2. And let's say I1 is still 1 amp. But now, let's say I have another wire tied in here at that node, and that is R3. And let's say I tell you that I have 1/2 amp coming through R3 in this direction. I3 equals 0.5 amps coming in this direction. All right, so I'm telling you we have 1 amp coming into this node here. I'm telling you we have half an amp coming out of this node through R3. And now my question is the same. What is I2? All right, so again, we're just using intuition here. I'm going to give you a way to write this equation later on in just a few minutes so that we can formalize this and solve things even when they're a little bit more complicated than this. But for now, I think that maybe you can use your intuition and you can say that, well, if I got 1 amp coming in here and half an amp coming out here, then I must have half an amp going through here, right? Because whatever's coming in must total what's coming out. And that's exactly what KCL says. All right, so I2 must be 0.5 amps. Because I got half an amp here, and that sums up to 1 amp here. It's just like if I told you that these are pipes, and I've got 1 gallon per minute coming through here, and then it splits off into 2 branches, and I've got 1 pipe coming off here, 1 pipe coming off here. If I told you that I had half a gallon per minute coming off here, then you would know that whatever's left over must be going through this pipe, which is another half a gallon per minute. All right. All right. So hopefully that is fairly intuitive. This is where it's helpful to have in-person class so I can see your head nodding or shaking. But I'm going to assume that this is fairly intuitive. Let me know if it's not, and I can go over it in more detail. So what KCL says, let's put it in words first. What KCL says is that the current flowing into a node and again, a node could be any place where 2 or more wires meet. The current flowing into a node equals the current flowing out of the node. All right, so sometimes you'll have several wires with current coming into the node, and sometimes you'll have several wires with current coming out of the node. So you say sum, here's another way of writing it, sum of currents in equals the sum, that Greek capital sigma just means the sum of everything. The sum of the current in equals the sum of the current out. Total current in equals total current out of any node. All right. Okay, so that was KCL. That's the brief motivation of KCL. Now I'm going to tell you how to apply these. All right. So here's a general procedure. Let's outline just a couple steps here for solving circuit problems. Solving circuit problems. Okay, step 1, I mentioned this before. Step 1 is just decide if you can solve it using the method of total resistance. All right, so ask yourself, can you solve with the method of R total? Combining resistances. Here's a pretty good clue. If you've only got one voltage source in the circuit, then there's a pretty good chance you can start at the far end of the circuit away from the voltage source and work your way back towards the voltage source, simplifying the circuit step by step. It might take 4, 5, 6, 7 steps maybe, but there's a pretty good chance you can do that if you only have one voltage source in the circuit. All right, so if you can, then start farthest away from the voltage source, combine into R equivalent 1, R equivalent 2. Keep track of what you're doing, like I was showing you before. Keep track of what R equivalent 1 represents and what R equivalent 2 represents, and so on and so forth. Okay? If yes, do it. If yes, do it. If yes, Do it. Do it that way. If no, then you're going to have to move on to a more sophisticated circuit analysis. So you're going to have to move on to KVL and KCL. You're going to have to use Kirchhoff's voltage law and Kirchhoff's current law. So if you're going to do that, so this is then step 2, is if you're going to do KVL and KCL. All right. So if you're going to do KVL and KCL problems, then you need to, first of all, label everything. So you need to label. Sometimes some of these will be given, but not always. Make sure all the resistances are labeled. Label all of the nodes. Those are places where the wires meet together. And this last one is probably the most counterintuitive. I'm going to write this and then I'll explain it. Assumed current directions through components, which for our case usually means resistors. All right. So where's that very first one that I drew? This was the first page. This was the first thing that I drew, okay, 10, 15 minutes ago, whatever it was. All right, so this is the one where I showed you we can't solve this using Ohm's law. So some of these things probably would have been given. You know, this would be V1. Sometimes I'll do VL for left, VL for voltage source on the left side, VR for the voltage source on the right side, and this might be given, R1 might be given, R2 might be given, R3 might be given. But what I'm saying here, to label everything, what I mean is, if these nodes are not already labeled, you know, this is a node right here that might be relevant for us. We might want to apply KCL at this node. So maybe we call this a certain node. Maybe we call this, here, I'm trying to be consistent. I'm going to do this example problem in a little bit. So I'm going to be consistent. So I'm going to call this node D. And maybe I want to call this one a node 2 also. This might be A, and maybe we'll call this one B, and maybe we'll call this one C, and then this one could be E. We may not actually need all of those nodes, but it doesn't hurt. So the nodes, and then here's the tricky one that you might not be familiar with. What we need to do in order to apply KVL and KCL, what you have to do is assume a current direction through these components, through these resistors, okay? Not the voltage sources, but the resistors. So you need to just guess. Use an educated guess, but it doesn't really matter. You just have to guess which way current is going to flow through these components, all right? And if you're wrong, it's fine. You don't have to go back and change it. Just guess, because that's how we're going to write our equations. So I'm going to guess that current is going to go this way through resistor 1. So I1 is going to go this way. I'm going to guess that I2 is going to go this way. And I'm going to guess that I3 is going to come down this way. All right. So that's what you need to do. You need to just make a guess, because that is going to determine how you write your equations, all right? And here's foreshadowing. If it turns out you solve everything, and let's say I3 turns out to be negative, it's no problem, no big deal. All that means is that actually your current was going the other direction. So no big deal, no problem. It just means that your initial guess was just flip-flopped. So just leave it like that. Don't go back and change anything. Just leave it as a negative current value. There's nothing wrong with negative current. Not like there is negative resistance. There is a problem with negative resistance. There is not a problem with negative current values. Okay? So we're labeling everything, including the assumed current directions, and then step 3 is to start solving by applying all the tools that you've got. So if you're at this step, you're probably going to have to apply KVL, KCL, but don't forget about the other ones. Just because you're using KVL and KCL doesn't mean that you can't, at some point in your problem, also use Ohm's law. Ohm's law still applies. You know, for example, if you get to a point in your problem where you know R1 and you know I1, then by all means, use Ohm's law to find V1. And the voltage divider, don't forget about voltage divider. Start solving the circuit by applying KVL and KCL and Ohm's law and the voltage divider. Use all the tools in your toolbox. Here's what you want to do to apply KVL and KCL. What you want to do is you want to look at your circuit, look for loops. So any loop. Let me give you an example. So a loop could be this right here is a loop. Similarly, this right here is a loop. Similarly, all around the outside, that is a loop. Similarly, this right here, the upper left, is a loop. Similarly, this right here is a loop, the right-hand side. All right, so any closed loop in your circuit will work. All right, so look for loops in your circuit or nodes. You know what? Let me write this as two different things because I don't want to confuse the issue. All right, I'll write nodes as a separate thing, okay? So look for loops with exactly one unknown voltage drop. Okay, so what I mean by that is, here's my example. If I knew what V sub L was, and I knew what V2 was, then I would look at this loop and I could say, oh, that is a good thing because I can write a KVL equation around this loop and I can solve it because I have only one unknown, and that would be V3. All right, so, you know, a basic rule of math, of algebra, is that if you have one equation and one unknown in it, you can solve it. If you have one equation and two unknowns in that equation, you can't solve it, right? But as long as we can write one equation with one unknown in it, we can solve it. So that's why you're looking for a loop that, you know, if you have a loop, you can write a KVL equation. You're looking for a loop with exactly one unknown voltage drop, which, by the way, could also be a voltage source. All right, you can find voltage sources this way too. So what we're trying to do here is find a loop where we can write a KVL equation where we can solve for an unknown voltage drop, like V2 or V1 or VL or VR. Okay, so that's what we're looking for to apply KVL. So this is equally helpful. Look for nodes with exactly one unknown current flow into or out of them, into or out of them. Okay, quick example, what I mean by that. Let's see, which one should I pick here? This is just an example, okay? But let's say we were let's pick node E for right now. All right, let's say that we are solving this problem and we are able to figure out what the current in this is going to be. This is not the best example because there's no load right here. But for the present example, let's just say that we're able to figure out what this current flow right here is, okay? And maybe we call it something else. But we know this current, and let's say we know what I2 is, All right, so if we know this current coming into E, and we know this current coming into E, then that's perfect, because we can apply KCL at node E, and we can solve for I3. All right, so what I mean is there's one current flow flowing into or out of E that is unknown, or any node that is unknown. So if I know this current flow, I know this current flow, I can solve for this last one. Or, you know, if I know this one and I know this one, then I can solve for I2. Okay, so I just need to have one and only one unknown current flow to apply KCL and construct a useful KCL equation. All right. Okay, so all right, you know what I'm going to do? So we're gonna do talk a little bit more about how to apply and write KVL equations and KCL equations in a moment. But quick mind break here. What I'm going to do is go back. I want to show you something for a quick mind break. Why? Because it's Wednesday, right? It's Wednesday, it's early in the semester, so it's time to watch something. All right, so here we go.
Uh-oh, guess what day it is? Guess what day it is? Huh? Anybody? Julie, hey, guess what day it is? Oh, come on, I know you can hear me. Mike. What day is it, Mike? Leslie, guess what today is?
It's hump day.
Woo-hoo!
Ronnie, how happy are folks who save hundreds of dollars switching to Geico?
I'd say happier than a camel on Wednesday.
Hump day!
Get happy. Get Geico. 15 minutes could save you 15% or more.
It's great. I love it. All right. You know what? Let's do a question. All right. So thank you for sending in those questions. You can still send them in if you haven't sent me that email that I asked you to do in the first video. So I have a question. Let me unbury it. It's under here somewhere. The question is, what's your favorite restaurant in Bloomington Normal? And let's see. Lots of the questions that you sent me, I've noticed, are difficult questions. There's a lot of restaurants that I like. I have to say I am a really big fan of pizza. I really like pizza, and so you know, I like deep dish Chicago style pizza. So Giordano's is pretty tough to beat. Giordano's is really good over there on Veterans, pretty much due east from campus, 2-3 miles. I also really like Blaze Pizza. Blaze is really good. It's a chain, so yeah. Well, so is Giordano's. So you know, it's not like this great local pizza you can only find here. But here's another thing that I really do like that is more of a local thing is Distill. Distill is a microbrewery. I guess it's a small chain, but they're headquartered here in Bloomington Normal. And one reason I like them is that their main brewery is probably no more than a mile from my house. It's definitely walking distance. I've done that. Walking distance to my house. So I really like being able to walk over to Distill, or I can ride my bikes. It's family friendly. I bring my kids sometimes. They have bags outside and big Jenga and things like that. So it's a very cool place. So I like to go there. They also do have pizza, by the way. And sometimes I order pizza there in addition to some of their home brews. And they also brew soda as well. So I get my kids soda and I get whatever their latest home brew is. They have some good stuff. All right, so that's good question. All right, so let's flip back over to the document camera. All right, so let's talk more about how we're going to write these equations. All right, so I don't know where my black marker went. It's buried under one of my papers over here. So for KVL, right, we're looking for loops. that have exactly one unknown voltage drop. So for KVL, to write a KVL equation, follow a closed loop. And you have to pick which direction to go. You're going to go clockwise, you're going to go counterclockwise. It doesn't matter, but you have to decide. It makes no difference. You get the same answer, but you got to pick one. So follow a closed loop, either clockwise or counterclockwise. And when you're writing the equation, when going with the assumed current direction. So this relates to that assumed current direction that you had to assume in step 2 up here, right? So you had to draw a little arrow next to the components to assume which way the current is going through the component. It doesn't matter if you're right or wrong, you just have to have that assumed direction in order to write a KVL equation. So when you're following along in your circuit, when you're going in the same direction as the assumed current direction with the arrow, then you're going to add the voltage drop and the opposite is true. When going in your loop, as you're following along in your loop, when going against the assumed current direction, subtract the voltage drop. So by voltage drop, I mean V1, V2, V3, so on and so forth. All right. Subtract the voltage drop. One more thing, we have to deal with voltage sources too. So let's say our loop includes a voltage source. All right. For voltage sources, like V sub L, V sub R, that kind of thing. For voltage sources, I'll give an example here. For voltage sources, take the first sign that you come to. All right, so as you're doing your loop, you know, there's a positive sign and a negative sign, right? So if you're doing your voltage, if you're doing a KVL loop like this, all right, let's say we assumed a current flow like that. Well, let's say you start here and you're going clockwise. So you would add this voltage drop because you're going with the current flow. So you'd have V, I guess we had total. So we'd have V total, and then we come over here. We come to the minus sign first before the positive. So we're going to say minus V, I guess this was maybe V total, minus V total equals 0. So that's kind of a self-obvious equation, right? V total, well, that's okay. Let's call that something different. This is maybe I don't know, V Alderman, okay? V whatever it is, minus V total, or whatever this battery is, equals 0. When we come back to our starting position, it's equals 0. Let me do another example here. Let's say we have VL. Let's say we have, this is resistor 1, and this is resistor 2, and this is resistor 3. And who knows what else is in this circuit, all right? We could also have resistors up here and over here and over here. It doesn't matter because I can identify this as a closed loop. So I can write this equation no matter what else is over here. So I need to assume current directions. So let's say in step 2 up here, I assumed that current was going this way and this way and this way, all right? That's what direction I assumed current was going. So you got to pick a starting place. Let's say we're going to start right here. Let's call that node A. So when you write this down, I recommend you write down what you're doing. KVL, and we're going to go clockwise from A. All right, so we're going to start at A and go clockwise. So when we do that, the first thing we come to is this resistor. The voltage drop is going from here to here, and that's with the direction of the assumed current flow. So I write V1. Then we come to this one, and we're going with the direction of the assumed current flow. So I just write V2, and we're adding it because we're going with the direction of the assumed current flow. Then I come over to here, and once again, we're going with the direction of the assumed current flow. So I'm going to add V3. And then I continue on in my loop, and I get to the negative sign first. So I'm going to subtract VL. And then I get back to my starting position, so I set it equal to 0. All right, so now if we wrote this equation and there was exactly one of these that was unknown, right? If any one of these were unknown, then I could write this equation and I could solve for that one unknown. Okay, so that's what KVL is. We'll do an example problem in a little bit, but you should be getting the feel for how we're going to apply that. And KCL is easier to describe. For KCL, it's easier for me to describe in words. All you have to do is write an equation with all current in to the node equals all current, maybe I'll add a flowing. Write an equation with all current flowing in to the node equals all current flowing out of the node. So let's say I had R1, R2, R3, R4, and in step 2 here, remember I had to assume my current directions. So let's say at that point, we just assumed, again, these are just educated guesses, or just guesses, and it's fine. Let's say that we assumed I1 was going left to right, I2 was going down, and we assumed I3 was going left to right, and we assumed I4 was going down. All right, that was what we guessed initially. So I'm going to write my KCL equation. Currents in equals currents out. All right, so what currents are coming into this node? We'll say this is KCL at node. Let's call this node A. At node A. All right, so what's coming into node A? Well, I1 is coming into node A, and I2 is coming into node A, and that's it, right? So I write I1 plus I2, that's my current in, equals my currents out. What's coming out of node A? Well, it looks like I3 is coming out of node A, and I4 is coming out of node A. So I write I3 plus I4. All right, and once again, if I was writing this equation, the reason I'd be writing this equation is because one and only one of these would be unknown, right? It only does you any good if one of these is unknown. So if any one of these is unknown, then you can solve that equation and you can find that unknown. All right. Okay, so that's basically what it is. In the next video, I think this is a good place to stop the video. I might make a couple of videos. I think I might make 3 videos today. This video was an introduction to KVL and KCL, and then I think I might make a second video with an example. solving an example, and then I think maybe I'll make a third video solving another example. All right, so let me, oh, there's my black marker. Let's go ahead and just write the circuit that we're going to solve in the next example so that you can start to think through it. All right, so I've already written this down. This was the very first circuit that I wrote, and I said, oh, we can't solve this using Ohm's law. So here it is. We're going to call this V sub L, and we've got a resistor right here, and we've got another resistor right here, and those come together. We've got another resistor right here, and we've got another voltage source right here. We'll call that V sub R. And then those meet up down here. So this circuit's not too bad. There's only 3 resistors, right? So it's not going to be that bad. So let's call this R1, and let's say it equals 10 ohms. And let's call this R2, and it equals 20 ohms. And let's call this R3, and it equals 30 ohms. So I'm trying to keep the numbers pretty easy to work with, all right? And a couple more things I have to give you. You don't have enough information to solve the problem quite yet. So the nodes I'm going to define, I'm going to define the nodes. I'm going to call this node A. And this is going to be node B, and this is going to be node C. Before I define a couple more, I mean, you could call that a node, you could call that a node, but the thing is that there's no component in here. So really, node B, really this whole thing is the same thing as node B, right? Because there's no component anywhere else in here. So this whole area right here, you could actually call node B. Same thing over here. Really, since there's no component in here, I could call this whole area over here. This is all really node A. And same thing with node C. Really, node C is this whole area down here. Okay, it's all at the same voltage because there's nothing to drop the voltage anywhere in this section down here. Okay, so there's our nodes, and I got to give you a couple more things. I'm going to tell you that, maybe I'll do it in a different color. Well, you know, all the givens are going to be in black. Let's do it that way. Everything that I tell you is going to be in black, and then when I solve it, I'll do it in a different color. Okay, so I'm going to tell you that I2 is going this way, and I2 equals 0.1 amps. That's a 0. 0.1 amps. Okay, that's given. And 2 more things are given. I3 is given. I'm going to tell you that I3 is going this way, and the value is also 0.1 amps. And the last thing I'm going to tell you is that ground is down here. So ground, there's the symbol for ground. Ground is at 0 volts. All right, so down here we tie the bottom of the circuit to ground. That means this whole area down here, including node C, is at 0 volts. All right. So if you want, what would be helpful for you is if you go ahead and try to solve this problem. That's why I wrote it out in this video. You can go ahead and try and solve this problem, do as much as you can, and then in the next video, I will solve it. Okay, so I'm going to switch over. Okay, so that was an introduction and a motivation of what KVL and KCL are. You've got an example problem to work on, so I suggest that you give that a shot. Try to find some loops where you have one unknown voltage source and or try to find some nodes where you have exactly one unknown current flowing into or out of that node. All right, and try to do at least most of that problem before you watch the next video, and I will solve that equation. I'll solve that circuit in the next video. So I'll see you then.